In today's video, we're going to explore redox reactions, which are chemical processes where both oxidation and reduction occur simultaneously. To understand these reactions thoroughly, we will examine displacement reactions, ionic equations, and half equations. We learned earlier that oxidation can mean the addition of oxygen to a substance, while reduction is the removal of oxygen. For example, if aluminum reacts with oxygen to form aluminum oxide, then aluminum is said to be oxidized. If we remove that oxygen and return the aluminum to its elemental state, then it has been reduced. However, oxidation and reduction can also refer to changes involving electrons. Oxidation is the loss of electrons, while reduction is the gain of electrons. To help remember this, we use the mnemonic oil rig, which stands for oxidation is loss and reduction is gain. This refers specifically to electrons. So, if a magnesium atom loses 2 electrons and becomes a magnesium ion with a 2+ charge, it has been oxidized. If that same ion later gains 2 electrons and returns to its neutral state, it has been reduced. Most redox reactions do not involve just one substance gaining or losing electrons in isolation. Instead, oxidation and reduction typically occur at the same time. If one substance loses electrons, another must gain them. Because these two processes happen together, the term redox is used, which is a combination of reduction and oxidation. Let us consider a reaction between magnesium and a dilute acid. The acid can be represented simply as hydrogen ions. The magnesium atoms will each lose 2 electrons, becoming magnesium ions with a 2+ charge, which means they are oxidized. At the same time, the hydrogen ions will gain those electrons and be reduced, forming neutral hydrogen atoms that pair up as hydrogen gas. Another area where redox reactions appear is in displacement reactions. These involve a more reactive metal displacing a less reactive one from its compound. For instance, looking at the reactivity series, we find that calcium is more reactive than iron. Therefore, if calcium is added to a solution of iron sulfate, the calcium will displace the iron. This forms calcium sulfate and solid iron. To understand these reactions better, we often write them as ionic equations, showing only the particles that actually take part in the chemical change. In our example, the sulfate ions do not change during the reaction. They remain as 2- ions before and after. Because they are unchanged, they are called spectator ions, and we can remove them from the equation. What we are left with is the simplified ionic equation showing the actual redox process. To go a step further, we can write half equations, which detail the loss or gain of electrons for each individual element involved in the reaction. For calcium, we would write that a neutral calcium atom becomes a calcium ion with a 2+ charge. Because it loses 2 electrons, we include those electrons on the right-hand side of the equation. This shows that calcium is oxidized. For iron, we write that an iron ion with a 2+ charge gains 2 electrons to become a neutral iron atom. Since it is gaining electrons, we put those electrons on the left-hand side, and this shows that iron is reduced. Each half equation must be checked for overall charge balance. In the iron example, the left side has a total charge of 0, made up of 1 ion with a 2+ charge and 2 electrons, each with a 1- charge. The right side has a neutral iron atom, which also has 0 charge. If the charges do not balance, it means that the electrons have likely been placed on the wrong side of the equation. That brings us to the end of this explanation. If you found this helpful, please consider sharing it with your friends and subscribing for more. We will see you in the next video.